Okay. Welcome, everyone. Thank you for coming. I know friends and family here and colleagues, and I think some friends and family watching online. So welcome, everyone. So normally at this time, I would provide an introduction to Rohan and his, all the usual stuff. But I thought it'd be fun to do something a little different today. So as some of you know, Rohan is a big trivia buff. He's run a number of trivia nights in Cambridge, and he's competed in trivia things, and he's done trivia at our group meetings. So to return the favor, I thought we would play a little trivia of Rohan. Here we go. So I thought we would do something like 2 truths and a lie. So basically this works is I'll say a couple of facts about Rohan, and you have to pick the lie. Okay? So we'll start with a warm-up one, an easy one. So countries that Rohan has lived: Germany, India, and Singapore. Anybody want to guess the one that's the lie?
Singapore.
Germany.
Interesting. Okay, keep track because we're going to have points at the end. Okay, so Germany was the lie. So Rohan was born and raised in India, and then went to undergraduate college at Singapore at the inaugural class of the Yale and U.S. College. So he lived in Singapore and India. Very good. Okay, so Rohan has written a number of papers, including 6 first author papers in grad school, and one of my pleasures has been reading those papers. And one of the things that Rohan and I often argue about is the language in those papers. As some of you know who've read drafts, he's a very colorful writer. So I thought it'd be fun to give a list of words that were used in Rohan's papers. And you got to pick the one that was actually not used. So protagonist, belly of the beast, rent asunder, and remarkably fallow. I'd like to guess which of those 4.
Protagonist.
So that was my son's guess as well this morning when I was running these by him. But no, that was actually used. So the answer is belly of the beast. Actually, when I gave this list to the family this morning, Riley, my son, said he wanted to write like you. So he got one admirer.
A 4th grader wants to write like me.
7th grader. Okay, things along these lines. Rohan is also very good at metaphors to describe his work, which I think is very important in the storytelling process. So these are some things, metaphors or just concepts, cultural metaphors or references that Rohan has referenced in papers or talks. Homer's The Odyssey, oligarchs versus democracy, the Celestial Monkey King, the book The Wheel of Time, and Bad Girls, the song by MIA. Any guesses?
Wheel of Time.
First one? No, The Wheel of Time, correct. Okay, here are some surprising facts about Rohan. He can program in IDL. He is obsessed with Korean dramas. And he does not know how to drive. Which of these 3? Okay. Things that Rohan has taught me. Rohan has taught me many things over the years. Here's a random assortment. How to program in Python. Texting slang. DTG, TMR, OFC. I've learned it all from Rohan. I've learned that you can call a Lyft ride from an interstate highway. And how to write trivia.
Well, you still don't know how to write.
That's true. This is a trick question. No, when we
Left right is true because I was there.
right. When we were driving in Arizona to visit the MMT, I was driving and nearly killed us all. We had a small accident, and Rohan, unfazed, whipped out his phone, and we got a lift ride and got out of there. Okay, I got to move on because I should actually let Rohan have some time to talk. Okay, some more words used in draft papers. I had to break this into two categories: christen, bespoke, and vast oceans. This one is a trick question, because all of them are used. Okay, Rohan's major contributions to astronomy include the Milky Way, the fact that the Milky Way halo is comprised of distinct structures. Rohan has argued, I think persuasively, that massive galaxies likely were the dominant forces behind the reionization of the universe. And Rohan discovered the first intergalactic asteroid. Which one do you think? We'll let that one go and answer. Okay, finally, things I admire about Rohan. Rohan has a really genuinely infectious excitement and energy that he brings to pretty much everything he does, and I can see it infect. I think it's probably not a great word to use, but I can see it infect the group, and it's really just exciting the way he brings energy to everything he does. He has a real childlike wonder and curiosity in the work he does, and I think that's one of the things that really enables him to make a lot of really exciting breakthroughs in the work he does. He has a really collaborative spirit. I think one of the things that's most interesting about his CV, in addition to having a lot of first author papers, he has 6 second author papers. And I think most of those, if not all, are genuine collaborative projects. He really enjoys the collaborative spirit. And then finally, the fourth, his passions are really not limited to astronomy. He engages with a very broad range of topics and issues in the world. You want to guess which one of those 4 is not true? That was not a trick question. Those are all. Okay, I'll stop and let Rohan take away.
Oh. Well, I was trying to save the acknowledgments and tears till the end, but that's not going great. But today, first, I'd like to tell you about an immigrant story. It's about our own galaxy, the Milky Way. I'm going to jump right in, and like I said, we'll save the tears for the end. Our story, our very broad story for how galaxies like our home galaxy build up, is kind of like this. It's not what you might naively expect. It's really messy. You have a lot of these immigrant, smaller galaxies that are all getting together at the center of the screen into this pile of jumbled mess. That you can't quite distinguish anymore what galaxy came from where. But of course, this is a simulation, and we're in God mode, so we are able to color every single particle based on its galaxy of origin. The key features I'd like to point out here is 1, there's many of them. 2, once these galaxies are disrupted and their stars are scattered all across the sky, there really is no way at first glimpse to tell them apart. And 3, I'll point out that there's a whole range of structures. There's stuff that is still in streams that's still being pulled out from their host systems. There's stuff that's much more mixed and completely disintegrated. And this is a story that has been in place for the last 20-ish years since the first lambda CDM models, cold dark matter models, were put in place and turned to focus towards what they say about the Milky Way. And since then, broadly, this is kind of like the picture we've had about how our own galaxy is built up. We know that as of today, at redshift 0, this present moment, when you look up in the southern sky, you see these galaxies falling in. These are the Magellanic Clouds. And there are many other satellites like these that we see at this moment that are falling into the Milky Way today. We also see some systems that are in more intermittent states of disruption. So the Magellanic Clouds are fairly intact, But this here, the Sagittarius stream, a very famous system that was discovered in 1994, the year I was born, so clearly I was meant to do this kind of work, is in this more intermittent state, right? We are seeing it being stripped live action movie of this process. And then finally, we expect that there's this really huge number of systems that have come in across the vast majority of our galaxy's history that are in this much more mixed and scrambled state. And this is what is going to be the focus of our talk today, of how do we recover what is essentially the bulk of our galaxy's history, of the bulk of systems that have come in and been integrated into the Milky Way out of this messy jumble. This talk's going to be roughly in 3 parts. First, I'm going to try and tell you what this mix looks like for our own galaxy, for the Milky Way. What are the individual systems that have been assimilated into the Milky Way over the last several gigayears? Then I'm going to talk about what my vision is for what we will do with that census. Okay, so we have these list of newly discovered galaxies. What can we learn about them? So let's get started with the first part. So all these incoming dwarf galaxies, all these incoming smaller systems that are being ripped apart, whose stars are being resettled across the Milky Way, we expect that most of them exist in this thin, shiny gossamer around the galaxy called the stellar halo. And the stellar halo is expected to have a very high fidelity memory of all these events for 2 reasons. One is the record of these mergers is preserved very well because of the relaxation time in the halo. From a purely dynamics point of view, this is a very nice movie that Anna made a few years ago, showing how a small galaxy is falling into the Milky Way. It's getting ripped apart, and this is in coordinates, in spatial coordinates, so x versus z, and you're seeing these stars being scattered all across the galaxy. But in the right panel, if you look at so-called integrals of motion, quantities like angular momenta, energies, actions, you see that even though these stars are being dispersed across the sky, they still retain some amount of coherence. Stars that came in together still retain memory that they were once part of the same group in these kind of spaces, even though they are dispersed all across the sky. So instead of looking for galaxies across the sky, as we typically do when we're searching for new galaxies, we can start looking for them in spaces like this. And we are still able to recover these very ancient mergers if we have access to these kind of integrals. Your mental model for what's going on here should be a lot like, one of these classical things that were drilled into us in high school about the conservation of angular momentum and energy, and the much abused example of the ballerina and the ice skater. When our physics teacher told me you should imagine a ballerina, I was like, I don't know what ballerina is, but I can imagine angular momentum. But here we have Yuzuru Hanyu very kindly demonstrating that through this whole sequence, they're conserving angular momentum by pulling their hands in together. And so their idea is, even though they're changing in these spatial coordinates, in these integrals of motion, they're a coherent point. The other thing that really helps us is that stars that were born in the same galaxy share very similar chemical DNA. And so even though they're scattered across our galaxy today, we can go try and measure this chemical DNA to associate them together. So the idea is that a galaxy that is more massive is typically going to be more metal-rich. A galaxy that may have been accreted very early in the universe may have more alpha elements like oxygen. Your mental model for what's going on here should be this. This is one of my favorite maps of New York City. And what it does is it breaks down New York City into the various immigrant communities, the little Italys, the little Indias, the Chinatowns across the entire city. And you see that even though these folks have moved around the world to call the United States their home, they still retain memory, cultural memory of where they're from, which is great, or else there wouldn't be much to eat in the US. But yeah, that's what's going on here. So these galaxies still remember, how to make biryani, how to make pierogi, how American pizza sucks, and so on. And so why haven't we done this, yeah? So like this theory, this idea that we can really recover the detailed history of the galaxy has been around since pretty much when I was born. But unfortunately, to compute these kind of integrals of motion, you really need full phase space data. So you need to know where exactly a star is in 3 dimensions. You've got to measure distances, positions on the sky. And you also got to measure velocities in all dimensions. And this is really tough. Similarly, you need chemical abundances to a very high precision to recover that chemical DNA that sits in each star. And this field has really taken off in the last few years, not coincidentally with when I started my PhD. I'm not taking credit for Gaia. I'm saying I exist because of Gaia. So the Gaia Satellite from ESA has really transformed this field. So in the last few years, Gaia has delivered precise positions, velocities, and is soon going to deliver even chemistry for order billion stars. And this is just instantly, overnightly transformative. But unfortunately, as transformative as Gaia is, it doesn't quite cut it for our purpose. And the reason is that all this beautiful phase space information arrives in perfect form from Gaia right away, only in this very local bubble around the sun. So if you're relying purely on Gaia to do this kind of science, to get all your distances, velocities, you can do that in a very limited volume. You can do it essentially for very bright stars, and this is not very helpful for our purpose, as illustrated in the simulated halo here, where if you're looking only at very bright stars, you barely get 10 stars in the halo out to 50 kbc. So what you really want to do is you want to push to fainter magnitudes. You want to capture this kind of exquisite phase space data, but in a larger bubble than the solar bubble that we are currently limited to. And that is why we initiated the H3 survey here. So this is a very long-term, large-scale project that's run out of Harvard and Arizona. Charlie here and Dennis Zaritsky at Arizona are the PIs who initiated the project. Anna here is one of our what is the title again? Survey doyens, one of the ARC eagles, one of the people at the top. And like any great survey, any great astronomy survey, we have a fairly contrived acronym. So H3 is hectoshell in the halo at high resolution. So we run this is a survey that's run on the MMT instrument here that while visiting which Charlie almost killed us. Here's Charlie and Nelson, actually, from that trip, gazing at the beautiful mirror. And the whole point of this survey, the key takeaway from this intro to H3 is that we're all about expanding that Gaia bubble, the bubble within which you have full phase space information, as well as detailed chemistry. We want to forge far beyond the local neighborhood. We want to forge deep into the halo so we can really begin reconstructing our galactic past. And that's H3's whole raison d'etre. And we're doing great. We've collected order 250,000 stars to date. I don't see Warren in the audience, so because our initial target at some point back in the day was 100,000 stars. So I'm sure Warren's been delighted that we keep upping it by 100K every new proposal cycle. And this is a survey that my thesis is based on. The whole promise of really understanding what's out there in the halo is finally in hand with this kind of data. And so the first set of results I want to show you basically gets at this question. What does this map look like for our galaxy? What are the various constituents that make up the Milky Way as it is today? And the approach that we took in this project was we really started out with the basics. We were like, well, is there even any structure out there? So here I'm showing you the kind of diagram that we just saw Yuzuru Hanyu in, the legendary figure skater. And what I'm doing is I'm slicing this data by metallicities. So that kind of chemical DNA that I was talking about earlier. So here are the most metal-rich stars, slightly more metal poor, the most metal poor stars. And the key takeaway from the slide is there is structure here. Each of these panels shifts quite dramatically as you move your eyes across this diagram. So in the top panel here, we see a lot of prograde stars. So those are disky stars, stars that are born with the same kind of angular momentum that the sun is on. But then as you move to lower and lower metallicities, you see things pop in and out, right? So you see that huge blob at the top. You see the central thing that we will soon give a very contrived name to. And you see they disappear from panel to panel. So there's a variety of spaces that you can see this in. But the point here is that the basic premise of disentangling various structure using these kind of spaces stands on pretty firm ground, clearly empirically. Then the thing that we do here is we try and isolate various structures. So we start with things that are known, and we then move our way to things that are unknown, and in the process discover a bunch of new dwarf galaxies that were not known earlier. So just to give you a taste for how this works, here's our familiar Sagittarius, born year 1994. Actually, no, born 5 gig years ago, but known to us 1994. And it's been studied for decades by looking for members across the sky. So you look in your deep photometric surveys, you see an overdensity, you go select those stars, and then you maybe do RV follow-up and stuff. But in the Gaia era, the way we are now able to study these things is using these integrals of motion, using these great ice skater quantities. So Sagittarius in particular, here I'm portraying a variety of spaces, like this familiar ELZ space that we saw earlier with our skater, velocities, eccentricities, various angular momenta. But the key point here is that these stars from Sagittarius form a very tight, coherent clump that you see in these kind of integrals of motion. And you can select it very cleanly using only this and no other on-sky information or any other such apparatus. And because of that, you discover new features, even about something that is very familiar and well known, such as this very low metal pore tail of Sagittarius that was not known earlier, that we speculated might be the stellar halo of a dwarf galaxy itself in a paper that Ben led a few years ago. Here's one of my favorite structures that I call Wukong. So this is a previously unknown dwarf galaxy that we found with H3. And we found it because we chose to look in this region of phase space where there were a whole bunch of globular clusters that we know were concentrated. And indeed, we saw a distinct population in a whole variety of spaces, including in actions and in metallicities as well. And the idea is you do this for everything you know, find things that you do not know, and then you're able to make a map like this. So this is what our galaxy looks like. This is one of the first maps really in full 6D phase space plus chemistry out to these distances of what our galaxy looks like. So here I am splitting up our galaxy in terms of these various constituents that we have isolated. There is this component called Gaia Sausage Enceladus. I do not take credit for that name. There's Sagittarius that we know and love. There's the high alpha disk, so the disk of the galaxy itself, the ancient high alpha disk. And here's another component that is also a Harvard discovery that Anna found here in 2017 called in situ halo. These are basically disk stars that have been kicked out of the disk into halo-like orbits. So this is something that had been speculated for a very long time, but we very clearly see it and map out its extent for the first time, clearly. And then there's a whole variety of smaller dwarf galaxies, some of which that we've reported here for the first time. But one of the key takeaways here is these three components really account for about 80% of the galaxy out to very large distances. And this really was a very fundamental prediction of lambda CDM, of cold dark matter cosmology, that there might be many dwarf galaxies that comprise the stellar halo, but there are a handful of them that dominate the halo by stellar mass. And so we see that very, very clearly here with this budget. We're also able to deliver a verdict on a whole variety of theories of how the halo was formed. So this has been a very, very lively topic for several decades. Like, how did this component of the galaxy form? Was it in situ? Was it ex situ? Were there outflows flung out by black holes? Were there a whole litany of them? And we really can't say that, well, actually, most of the halo is comprised of a handful of these dwarf galaxies by mass, and even the rest of it by these smaller dwarf galaxies that we found, some of which we found here. In the process, we also solve a lot of good old long-standing puzzles. One of them is about how the Milky Way used to appear quite weird compared to a lot of stellar halos that we observe in the broader universe. So the Milky Way halo used to appear off this kind of relation, far away from similar neighbors, very far away from M31. And with this new survey, we really can recalibrate where the Milky Way lies, and we see the Milky Way halo is really much more metal-rich than it was thought earlier. And the way to understand this is directly from our senses. If the halo by mass is built out mostly by a handful of relatively massive dwarf galaxies, you do expect the halo to be quite metal-rich. We also are able to put together a unified origin story for the bulk of the halo. So before we started doing all these angular momenta kind of things with Gaia to try and find these structures, we used to look hard at the sky and try and find streams, thin streams like this, over densities, and a whole variety of other, a whole zoo of structure in the galactic halo. And one very neat result, working with Anna over the last few years, has been that we really are able to tell a unified origin story for a vast variety of structure that has been cataloged across the last 2 decades in the form of globular cluster streams, halo globular clusters, over densities here and there. I'll talk a bit more about that in a bit. As being consistent with having arrived with these dwarf galaxies that we found in our census with H3. So where do we go from here, right? So we have this census of dwarf galaxies, many of them seen and characterized for the first time. But what do we do with this? Is it just stamp collecting? Are you just happy to add yet another stamp to the collection? Some people would say yes. I'm inclined to agree, but here are some interesting things I think we really can learn from this new census of dwarf galaxies that is emerging, the dwarf galaxies that are dissolved in the halo. The basic idea here in this part of the talk is that we are now in an excellent position to go from this illustration of the Milky Way that I've been showing you, that I'll call the classical spherical cow Milky Way, where you have this very nice, beautiful, gorgeous halo that's spherically symmetric. You're sitting in an NFW dark matter halo that's also symmetric and such. We can now get much more grungy and gritty about what's actually going on, where we can start thinking about the Milky Way as the sum total of these individual events and even start modeling it as such. And the reason you might want to do this is you could say that, well, these things are actually not bringing in too many stars, right? As a function of the total mass of the galaxy, the stellar halo comprises less than 1%. So who cares whether you have a gritty, realistic portrait or you're a spherical cow? You can very happily be on the spherical cow team. But one reason you might really care is that these systems bring in a lot of dark matter with them. So the stellar to dark matter ratio in these smaller galaxies tends to be much lower than in the Milky Way. In fact, many models predict that the vast majority of dark matter in the galaxy might actually be accreted in these individual events. So if you're interested in dark matter around the galaxy, if you're interested in the nature of dark matter, trying and maybe detecting the particle and such, and all the reasons dark matter enraptures us for so many decades, then you really got to care about how it's distributed, because it's not distributed like your spherical cow. And any such story has to start to take into account this very, very massive merger, the last major merger, that I will refer to as GSE for the rest of this talk, that really comprises, and we show this very cleanly, the bulk of the stellar halo in the inner galaxy. The inner halo can really be thought as GSE to first order. And we've learned a lot about this particular system with H3 in particular. I'll just go over some of the constraints that we, I think, have very robustly and uniquely derived. So one of them is the timing of the merger. When did this very massive, very significant event in the history of the galaxy happen? And we're able to constrain this by just looking directly at the age distributions of stars from this particular event. So you look at the age distribution of stars from the GSE dwarf galaxy, it's consistent with being truncated roughly around 10 gigayears. And very consistently, you look at the age distribution of stars that were kicked out of the Milky Way's disk during this particular merger, and there's about a 2 gigayear offset signaling that that's roughly when this merger ended. So we have a very good sense of when exactly this very significant event in our galaxy's history went down. We also have constraints about the initial orbit of this merger. So we uncovered extremely retrograde debris that we call Arjuna in our first paper, that turns out to be quite chemically indistinguishable from GSE. So we think it really is the most retrograde debris from this event. So we get a lot of information about what the geometry of this 10 billion year ago cosmic car crash may have looked like. Namely, this galaxy came in on a retrograde orbit. So there's this key piece of information is something we've recovered from history. And of course, we've also charted the debris across the galaxy. So this map really stretching into the distant halo is something S3 has, I think, very novelly established, not just in some kind of density map or any other photometric way, but cleanly with chemistry and all this dynamical information. So one of my key pandemic projects was to sit at home and crash galaxies into each other again and again and again and again. And the idea here was to try and work out a configuration that matched what we were seeing in our data. So I basically set up this galaxy merger factory in our bike room and just spent all day like throwing galaxies at each other. And the idea here was to run a whole suite of these simulations that started from what we thought were realistic guesses of what things looked like 10 billion years ago, to see if we could get something out that matched our data. And remarkably, we were able to do this. Oh, I see. You all are laughing about the bespoke. Yes. Yes. Out of this ocean of simulations, this is the chosen, christened one that emerged. And it said 20% of the Milky Way's dark matter came in this one merger, which is really remarkable, right? Like, again, I find this really mind-boggling. This is something that happened 10 billion years ago, like this cosmic car crash. And we're backing out the geometry. We're saying that, this thing fell in at a 15-degree inclination with a circularity of 0.5, 10 billion years after all this happened. So, yeah, I think that's pretty cool. And yeah, one of the key takeaways from this experiment was that, indeed, about half of the Milky Way's dark matter appears to have arrived in these three distinct events: the GSE merger, Sagittarius, and the Magellanic Clouds. And so any fair accounting of what the dark matter in the galaxy looks like needs to take into account that it came in along this very particular orbit and is arranged in a very particular way that is definitely not spherical cow-like. And thanks to this model, we learn a lot about what actually is in the galaxy, why it is the way it is. So one such example is that we've known for a long time now that the shape of the inner galaxy it looks like a blimp or a zeppelin. It's this triaxial shape that's stretched out kind of like this. And the question is why? And it turns out that you get a very nice, elegant answer from this reconstructed simulation. And it basically is the orbit that this galaxy fell on. So it's coming in here, time t equals 0, does this swoosh under the plane, goes up again, and the vast majority of stars are lost along this axis. And it turns out that this same exact axis is the major axis of the blimp of the inner galaxy. So we get this very nice explanation for why the inner galaxy looks the way it is. And it's because that is the axis along which the orbit of this merger ended. You also get an explanation for some of these like really massive clouds of stars that were found 10, 20 years ago with SDSS. So we see that even though this set of simulations was not tuned to match this at all, we see things like the Virgo overdensity and the Hercules Aquila cloud that have been known for a long time. It turns out that these are just very natural outcomes of this GSE merger. And once again, we can explain them based on the turning points in this orbit that we backed out about this 10 billion year ago cosmic car crash. And then another very exciting result in the same vein is that it's not just the stars in the inner galaxy, but the dark matter halo itself that is also tilted along this same axis. So this was a very, so this is straight out of the simulations, but Jesse Hahn, who's here in the audience today, wrote a very creative paper also looking at the stars to explain why this might indeed very well be the case in the Milky Way, even if you don't believe my simulated universes from my pandemic year. But yeah, that's kind of where I'll leave this work at, on the note that we really are beginning to build these very realistic models of what the Milky Way actually looks like. And we're just getting started. This was the largest chunk, the one that we had all these constraints on, but there's much more to be done. Now I want to shift gears a bit to what I call near-field chemical cosmology. I'll explain what that is in a bit. So one of the real great privileges of doing astronomy is that you're not limited to the present epoch in terms of what you can directly observe. What that means is that you can simultaneously perceive various epochs of the past stretching all the way to the Big Bang because the light from those events has taken so long to get to you that they're still carrying news of what is the past. So everything is happening everywhere all at once. An imperfect metaphor, which is to show you that I'm very locally acculturated, is that imagine you were like peeking out of this window, and like close to the window, you saw the great Brady winning his first 2001 championship for the Patriots. Slightly far away, you saw people dunking tea into the sea during the Boston Tea Party. And even farther away, you saw the dinosaurs roaming the earth while looking out of the same window. That's kind of what we're doing. And it's one of the great, one of the things that honestly got me into doing astronomy. I just found this mind-bendingly beautiful. And so one of the first papers I wrote, not one of the first, the first paper I wrote, if you're watching Pascal, thank you. This is one of my favorite galaxies. It's called GS30668. And this is a galaxy that lies at redshift 2. So we are directly witnessing what it looked like essentially 10 billion years in the past. The thing I'd like to highlight here is while we have this great privilege and opportunity to look back into the past, doing so is very, very difficult. Right? Like imagine all the grandeur and beauty of the Milky Way compressed into essentially like 8 pixels on a CCD chip. That is what we're working with. But with this business of looking at immigrant galaxies and the tales they bring to us about the early universe, we have a very unique opportunity here, right in our solar neighborhood. The idea is when these immigrant galaxies merge with the Milky Way, at whatever time in the past, they are rent asunder, and their stars are scattered all across the galaxy. And when that happens, they stop evolving. The interstellar medium in those galaxies is completely disrupted. So all the chemical abundances of those stars, all their properties are kind of frozen in place. So in many ways, when we're cataloging the debris from these systems, we really are putting back together a galaxy as it was at very high redshift. So we are able to do that everything, everywhere, all at once kind of thing, but in our local backyard. Here's a trivia question for you. If somebody asked you, what is the nearest galaxy to us? That is not the Milky Way. Some of you might answer Segway, which is about 20 kbc away. Some of you might answer something else, but I can't say anything about it yet. But maybe you might hear about it soon. But one possible answer that would be difficult to contest is our favorite Redshift 2 galaxy, GSC, because we are sitting right amidst the debris of it. We are sitting within the debris field of this Redshift 2 galaxy. And this makes it ridiculously convenient, right? So if you're doing spectroscopy, even if you're somebody who's used to doing spectroscopy of these dwarf galaxies in the Milky Way, often you're in a situation where I've been at telescopes where people have I've watched people live making this calculation. Oh, we have maybe 3 giant stars that we could target in 1 star per night each across this entire run. That is kind of the mode in which people operate with when they're studying these other satellite galaxies in the Milky Way. But just sitting within the debris field of something around the sun just lets you catalog thousands and thousands of stars in almost no time. And we're already there. Some of these systems are already the most studied extragalactic systems, if you may, that we've ever collected data on. We have thousands of high-resolution spectra on essentially these high-redshift galaxies, and we can use them for all sorts of things. So I'm just going to give you a taste of the kinds of things I've been trying to apply them to, and we'll solicit more ideas about what we can do, because I think we're just really getting started with this sort of way of thinking. So here's something we tried recently in a paper called Live Fast, Die Alpha Enhanced. This was the MIA reference. And what we've done here is we're looking at the mass-metallicity relation. So this is a very famous correlation that we observe for galaxies pretty much everywhere, where your stellar mass, how many stars you have in a galaxy, is strongly correlated with what your metallicity is. And this has been tough to establish at these very low masses. So we are talking masses far less than the LMC even. And this is tough to do even at redshift 0, forget at high redshifts. And so this is if you look at the science case of the ELTs, of the extreme large telescopes that are being built in Europe, or that might, no comment, that are being built. This is one of the things that we hope to do with them, right? We hope to measure the stellar mass, stellar metallicity relation for very low mass galaxies at high redshift. But that is something we can already do with this kind of hack that we found by bringing back the stellar halo together. So most of the systems I've cataloged, we think were disrupted around redshifts between 1 and 2. So we really are getting a read on what the mass-metallicity relation looked like at these early epochs for these low masses that are very difficult to access. Similarly, we get a sense of alpha enhancement. So this is a plot showing your alpha elements, so elements like oxygen, magnesium, as a function of how offset they are from this redshift 0 MZR, which correlates with their redshift. And we see this very nice relation that unites not only the disrupted dwarfs, but also the surviving satellites of the Milky Way, leading to this very neat conclusion that at redshifts of 2 or 3, galaxies must be alpha enhanced by a factor of between 2 and 3. And this is super exciting that we can back out this number, because this is pretty much the number that people find by doing very deep, detailed spectroscopy of distant galaxies directly. Except we are able to do this for very low mass galaxies. And so this is, to somebody who comes to this from a high redshift galaxy evolution point of view, this is all sci-fi, right? This is all sci-fi. If you're able to detect alpha enhancement in order 10 power 7, 10 power 8 galaxies at redshift 2 to 3, yeah, that is a voice from the future that is speaking all these results. Here's another sci-fi thing that we were able to do. We were able to reconstruct the metallicity gradient across the disk of a high redshift galaxy. So remember this particular image. This is the kind of high redshift galaxies we're talking about. So imagine measuring a metallicity gradient across this image, right? That is the measurement we're talking about. People do it nonetheless, even though there's 8 pixels there. That has never stopped anyone. Here's another way to get at this. So the simulations I was showing you earlier about this Redshift 2 galaxy being disrupted, we can back out this very neat correlation between what your motion is in the Milky Way today to where your location in the original disk was. So the idea is, in this original disk, the debris from the outermost regions was stripped first on these very high angular momentum orbits, and the remaining core of the galaxy, the center of the galaxy, survived till the very end and was stripped on a very radial orbit. So that's what our simulations show. And so we can back out this very neat mapping between where a star was in the disk to where it is in the Milky Way today after being resettled. And so this lets us measure a metallicity gradient, which we find to be quite flat. In case you were thinking that's very underwhelming for somebody searching for gradients, it's not. Because this is something that's been predicted for a while, that at high redshift you expect fairly flat gradients, and only at lower redshifts do gradients develop to be stronger. And there have been suggestions of this by using gas phase metallicities, but we see this in stellar metallicities for the first time. Another fun application that we've found for using these high redshift dwarfs is to try and cast some light on what the source of heavy elements is. So you may have heard of Carl Sagan's famous quote about how we are all made of star stuff. This is what he meant, right? So this is a periodic table, except here it is colored by where we think these elements originated in terms of their astrophysical origins. So you see hydrogen and helium kind of were the starting Ur material out of which everything came. But then we have a very good origin story for the vast number of elements on this chart here. We think, things like magnesium and oxygen came from exploding massive stars. Things like iron came from white dwarfs. But there's a whole class of elements here colored in orange whose origins are currently being debated. And kind of like the two channels that are the leading channels for a variety of reasons is neutron star mergers, the kind that we were very lucky to perceive both in gravitational waves and as a kilonova as well, or some kind of special, very energetic type 2 supernovae, a core collapse supernovae. And the key idea here is that these core collapse supernovae go off right after a star formation event, almost correlated. But it takes time for the neutron stars to first form and then to merge and produce a very energetic kilonova. And so what we can do with these disrupted dwarf galaxies is we can exploit these different predicted timescales for these two channels to try and see which one is right. So what we're doing here is we are looking at these heavy elements symbolized by europium, which is everybody's favorite heavy element, divided by magnesium, which is produced only or almost predominantly in core collapse supernovae. And the experiment that we are able to craft here is to look at two different dwarf galaxies, two different disrupted dwarf galaxies that we have a lot of data on. One of them is called GSE, one of them Kraken, and the key thing here is both of them have very similar stellar masses, but they compile their masses across different timescales, roughly a factor of 2 in timescale. So you get to the same mass, but you get there faster. You get to the same mass, but you take more time. And so what you can then do is you can go and decouple their heavy element patterns to see what the channels are that are producing those elements. And you find a very interesting, very surprising answer. We find that neutron star mergers that a lot of folks believe are really the dominant channel actually require a very high delay time, about a gigayear, to really explain this kind of enrichment pattern. So the idea is that at very early times, these rare core collapse supernovae really dominate your heavy element production, and then in later times, your neutron star mergers take on. And this is a very, very unique constraint that we're able to place thanks to these disrupted dwarfs. And very suggestively, I've shaded these various regions here. So all the folks on the MIT time allocation committee, the CFA time allocation committee, we'd like to get data for these as well. Okay, that's what I've got for you today. I'll leave you with a quick summary. We really are in this new era of cataloging these disrupted dwarfs that have that are so central to the history of the Milky Way. We have already cataloged more disrupted dwarfs, most of them discovered in the last 2-3 years, than the known surviving dwarfs. That is about the H3 survey completeness limit. So just to give you a sense, like, the Magellanic Clouds have been known for decades. Like, all these systems have been found over the last, century plus. In 3 years, we've found more systems than we've compiled across, essentially human history. So we're just getting started. We can push to lower masses. We can push farther out in the halo. Vedant here is already doing some really excellent work on this, like what lies beyond 50 kpc. What's out there? We're getting to more and more realistic models of what the galaxy looks like. So this is some really excellent work that Harvard undergrad Katie Sharp is doing. We now have this really gritty, gory picture of what the Milky Way actually looks like, and not just a suggestive simulation that I opened this talk with. We actually kind of know what's out there now. And finally, this whole business of near-field chemical cosmology is just getting started. Like, so many of these examples that I showed you were really arguments that didn't quite exist. We had to articulate them for the first time, and there's many other arguments out there waiting to be made. I know, for example, that there are people here in this very room also who are excited about finding planets around some of these accreted galaxies. Wouldn't it be cool to find a planet around a star that is not born here, but somewhere else? What could we learn about it? And so we're just getting started with this as well. Okay, what have you been waiting for? Acknowledgements. I'm going to spend a few minutes doing this. I'm going to start with Charlie. The first thing I learned about Charlie, looking at his website, was a pointer to this long blog post from some random marine biologist at Duke. So clicking on this link, okay, you find this great essay about how crazy an idea it is to pursue a career in academia. There's so many jobs, there's so many people graduating, why are you making this life choice? And then somewhere, along that essay, there is, choose your advisor wisely. And then at the end of it is okay, if you made it through all this, then okay, write me an email. So I did it, and I'm very happy to say that, I chose well. And it's been such a great time for a whole variety of reasons. But the one that I'll highlight the most is that throughout my PhD, I have always felt like an independent researcher, right? Even though at the beginning I might have been a very stupid independent researcher, I was allowed to be an independent researcher. My ideas were always given weight. They were always gently explained as to why they might be asinine. But they always had room to grow, and so much of why what I've done across my PhD has worked out is because for every one that worked, we were able to iterate through 20 of them. And I always felt comfortable sharing them, and yeah, that's kind of how we've submitted roughly one telescope proposal a semester for the last 5 years, including to the CFA, to HST, to JLST, to everywhere. Very grateful for professors who've taught us everything we know here. My committee in particular, Daniel, Doug, Lars, Catherine. I came away from all our meetings always feeling like I was working on things that mattered, that made people that I looked up to excited as well. None of this would have been possible without the H3 survey team, all of whose very beaming faces I have cannibalized from the internet here for your viewing pleasure. But no, we're more and more moving to an era of like big science, right? Like huge teams, like multi-institution collaborations, like ridiculously like, we're moving towards that CERN high energy particle theory kind of stuff. So in that era, it's really remarkable how much we've done as a team of a dozen people. We do everything ranging from designing target lists to reducing the data, to fitting parameters, to writing all these science papers, figuring out what's happening. All of it, all the action happens here. And so none of this would really stand without all of you. I've been really grateful to have such an amazing home base across the years in Conrad Group. And I was just looking through this list, and I really was able to overlap with almost everybody here on this list. And right from day zero, Conrad Group has made me feel so welcome. Like, I remember in my first year, I took this, when I was feeling very homesick, I took this long road trip with June and Alexa. And that was one of the first times I really felt like, things would work out in the US. I'm very grateful for all the postdocs and research scientists at the CFA. The amount of time I've spent camped out in your offices is almost comparable to the amount of time I've spent sitting in my office, to the point where I even remember getting complaints from people at some point that why is Rohan in your office all the time? Like, why do we hear his voice? And so yeah, this has been a huge reason why I've had such a good time here, all of you, listed here and also pictured here. So much of the work that I've done in recent years has been because of friends I met on the sidelines of conferences, collaborators, people who I just got along with, and that has been one of my key takeaways, right? Like, when you're working with friends and people you like, everything is fun. For example, the whole heavy element thing that I described came out of hanging out with Alex G on the sidelines of conferences. 2 papers and JLT proposals that I wrote came out of, hanging out with Yorid Mate over here, who also turned out to be a liberal arts college graduate who loved doing astronomy. Pascal has been around since day zero, since that 2017 paper that I told you about with my favorite Redshift 2 galaxy, Nico Gertina. The students in the department have made such an amazing, collaborative, welcoming atmosphere that I think is symbolized greatly by Claire's cookie that contains one of my favorite plots that she hand-delivered to my door during Christmas, during the pandemic year. That I think really symbolizes the spirit of the students here. The Astro Department admin, without which all the miracles that happen here would never happen. Peg, Rob, Lisa, Stephanie. Again, right from day zero, right? Like, when I was first trying to get here, my US visa was declined and thrown in some kind of crazy administrative doldrum. And I remember Peg and Avi got together and just wrote all these very, in hindsight, funny letters about how dare you not let Rohan come here? You can imagine Avi arguing for that. All the friends around Harvard, around GSAS, around Ashford, this has been one of the main reasons I've managed to stay happy here, by dragging all of you to all the various trivia nights across town, despite all your kicking and screaming. We would even do HQ trivia every night, actually, and at some point we had a 5-win run, which was great. We made $2.50. Total, not per person. So many of my Yale and US and Yale friends watching, some of whom are here, I've been so grateful for your company over the last few years. Especially during the pandemic. I'm very grateful to my professors at Yale and US. They're 99% of the reason why I chose to go down this path. Just seeing how passionate they were, how engaged they were, how much they gave themselves to mentorship, and how much they enjoyed it. In particular, shout out to Charles Balin here, who, despite being the one astronomer on the whole island of Singapore, still somehow managed to get some of us to pursue professional astronomy. So I guess well done, Charles. Then all the folks at Yale Astronomy. So I spent a lot of time as a visiting student at Yale as an undergrad, over a couple summers as a visiting junior, and I had such a great time in that department. Without which I would definitely not be here. Shout out to so many of my friends, mentors, supporters from Hyderabad, some of whom are here, some of whom are watching. You've been around since day zero, and now we're here. My family back home, who I haven't been able to see in a few years now. Particularly my mother. The first PhD thesis I worked on was actually on the financials of paper mills in the southern part of India. It was my mother's PhD thesis. I was 10 or 11. We used to go to these cyber cafes, pay 10 rupees an hour. I would sit there typing up Excel spreadsheets, calculating sharp ratios, doing all that kind of stuff. And we didn't quite make it, My mother gave so much of herself to raising us that she couldn't quite, we didn't make it. We couldn't finish that dissertation. So this PhD is really dedicated to her. Acknowledgements to the Peters family here in the US, who really not let me feel the absence of not having seen my family for the last 2+ years. And finally to Michelle, who is here in this great photo sequence. There's actually even 3 more rows on my camera roll. No, it is in Shanghai. It was a rainy night, and we were waiting. I don't know what we were waiting for, but this is a great outcome. But no, to Michelle, really, as I say in my thesis, it's difficult to thank you for anything in particular, because I must thank you for everything. And that's that. I'll take any questions, starting with about what's been clipped off. But yeah, that's that.
Went to this next slide. Obviously, planets around stars from another galaxy would be great. But, I think asteroids is really where the edge is at now. So tell us more about those prospects.
About what prospects, sorry?
Looking for intergalactic asteroids.
Well.
Just kidding.
I'm going to pass. I think it's Anna asking me something smart, actually.
Any other?
Yeah, in that line of questioning, can you back up 3 slides, go and look at the family picture.
My family picture?
Yeah.
Yale and US family, or no? Sorry.
You did not identify yourself.
Oh yeah. Any guesses? Well, it's this stereotypical nerd. What box are these? It's me over here, and that's. It took quite some searching to
So
find.
I was wrong. Was anybody else wrong about that?
So a red shirt.
That's my younger brother.
Yes.
That's my younger brother. I'm sure he was very flattered. Arjun.
Sorry, I'll ask a boring astronomy question.
First, I must apologize that the structure clearly named after you has been swept into GSE, but
Yeah, very peculiar and retrograde. When dark matter to stellar mass ratios, especially reconstructing them from these from the orbits of the stars, how robust is that, the derivation of that ratio? Because at least from the M31 perspective, it seems like the dark matter to stellar mass ratios vary quite a lot and produce the same kinds of morphological or maybe even magnitudes. I was curious about your concept.
Yeah, I think cumulatively for the total dark matter halo, what actually ends up mattering is these handful of big things that you get. And so in our case, it is the LMC, Sagittarius, GSE, maybe something before that. So it really is what the ratio is for those big things that really sets everything. Like in terms of the total halo mass. If you care about like direct detection experiments for like particles within the solar neighborhood or something, you care about smaller streams and stuff like that. But for the total halo mass, it really is those biggies that are setting that. So my guess would be that for M31, even though the total mass works out quite similar, and even though the stellar halo is much more massive, that these large major events might end up being comparable in terms of how much they brought in. From a simulation perspective, this is definitely uncertain. It's one of the we try various ratios, right? Like we try more massive ones, less massive ones within some range, but indeed that is degenerate with what you assume for the Milky Way of that time as well. So I would say the ratio, the mass ratio, is more immune than to the total mass at that point. But still, I think it really modifies the geometry of the debris that you see. So there is information that really can constrain this. Because for the overall dynamics, right, like it really is the total mass that's setting all that. Like the decaying orbits and the things that I showed, that really is set by the total mass. So I would say that in some ways, we are more sensitive to the total mass than to the stellar mass from a dynamics perspective.
All right, we should probably leave it there, I think, because we have to move on to the private defense and other activities. Before we thank Rohan, so the committee will convene in about 15 minutes in Pratt, right? You have Pratt, I think?
Yes.
And presuming that goes well, I don't want to be presumptuous, but presuming it goes well, we will have a champagne toast at 3:30 in the lobby downstairs, because there's an earlier celebration at 1:30. So if you want to join us, we'll have champagne and some treats at 3:30. With that, let's thank Rohan again for a great time.
That's great. That was very, very